The actual equation is F is equal to K BIL sine theta. K takes value 1 through the definition of the Tesla. So the magnetic field or the magnetic flux density, which is also another term that is used, magnetic field or magnetic flux density is to be measured in Tesla, current in amperes, length in meters, and when the angle is 90 degrees, then you can get the maximum force coming out of it. So the maximum force is when you have at 90-degree angle. So when the current and magnetic field, when they are at 90 degrees to each other, you can get the maximum force, which is this, BIL. Okay? Maximum force is BIL. Now, look at this conductor once again. That's a conductor that is carrying a current. Now, the current is going that way. And let's say the magnetic field is into the board. The magnetic field is into the board. And the current is going in that direction. That's what we are trying to do. Force on moving charges. So if there's a current flowing in a conductor, we already know that there's a force acting on it, which is BIL sine theta, right? So we know that part of it. Now what creates a current? How can you get current in something? What should happen first? Yeah, potential difference is required for a current to flow through, but what exactly is current? What's the definition of current? Rate of flow of charges. That means there must be flow of charges. So if a current is going this way in a metal, what actually is flowing in this? What is flowing? If electrons, which way? Opposite way. So there are electrons moving backward this way, which actually creates a current. The electrons are moving in this direction, creating a current. Now the electrons are drifting with a velocity of v. The electrons are drifting with that velocity v. Is there any relationship between this current and this drift speed? Yes?
Yes.
What's the equation? The drift current in terms of drift speed. We have gone through that equation. Drift current I is equal to NAEV. Right? We've seen that equation.
Yeah.
Drift current is equal to NA. What is N standing for? What small n standing for?
Is it number of electrons?
It's not just the number of electrons. The total number of electrons is N, capital N. But what is small n standing for? Yes.
Number of electrons per unit length.
Per unit volume. So N, small n, is the number of electrons per unit volume. And what is the volume? If the area is A and the length is L, what's the volume? So let's say, back again, there is a magnetic field into the board. and an electron is going that way or entering the magnetic field. An electron is entering the magnetic field, so an electron is shot into it with a speed v. So that's an electron. So if you shoot the electron right into the magnetic field, what will happen to this electron as it enters the magnetic field? What should happen? So, or imagine you're shooting a magnetic field, you're shooting an electron all inside the magnetic field. Like for example, in this room there is a magnetic field, right? Which way? Which way is the magnetic field in this room from the earth?
That way.
Yeah, that way, but kind of dipping this way, right? So let's say you're already here and you're shooting an electron. So an electron is shot in that direction. So which way will it experience a force?
Yeah.
Downward. Good. So electron is going that way, the current is this way, magnetic field is in, so it experiences a force downward. So what will happen to the electron? Will it start moving down? Remember, it is moving that way. It's moving that way. What's going to happen? It's going to turn. Now, which way is the electron moving when it is here? This way. Electron's direction has changed. So which way is the force acting on that? Which way is the force going to be acting on this one? So since the electron is going that way, the current is that way, and the magnet. So it will be this way. What will happen because of that force? It will deflect further. Then the force will be in this direction. It will deflect further. Then the force will be in that direction. And it will keep deflecting, deflecting, deflecting. Can you tell me another name for this force? Centripetal force. That's a centripetal force. So the magnetic force is the centripetal force which kind of takes it round and round through a radius r. The magnetic force is what takes it round and round through a radius r, providing the necessary centripetal force for it to go on. Can you recollect the centripetal force formula? What's the formula for centripetal force? Oh, you have
MVR.
It's mv omega. Anyone? Just out of your top of mind. Remember from last year, what is centripetal force formula?
V squared over R.
That is the acceleration. So what's the force? mv squared over r. That's the formula. So the centripetal force is provided by the magnetic force. And this magnetic force is BQV. So BQV is equal to mv squared over r. So what is one of the v's cancel off? So magnetic force is equal to centripetal force. Magnetic force is equal to centripetal force. And so one of the v's cancels off. So what is the radius of the turn that it's going to take? Cross multiply, you got mv over. That's an important equation. So when a charged particle is shot into a magnetic field, it is not going to go straight. It's going to keep going in circles. It's going to keep going in circles. Of what radius? Radius r. Now the radius r depends on what? Depends on the mass of the charge. So if you're talking about electrons, it's going to take quick turns because mass is too small. Now if you're talking about a positively charged ion, then it's going to take a bigger turn because the mass is bigger. Of course, it depends on how fast it's going too. Now, Compared to shooting an ion, an electron can be shot much faster because it's lighter. So you can have an electron going spin. So the radius is proportional to the mass. The bigger the mass, the bigger the turn. Radius is proportional to the speed. If it is going faster, it's going to take a wider turn. Radius is going to be smaller if the magnetic field is stronger. So if it's a strong magnetic field, it will turn it pretty quick. And also the charge. If it has got more charge attached to it, it's going to take a smaller turn. You see it? So instead of like singly charged, if it is like charged multiple times, then it's going to take a radius smaller. Okay. So radius of the turn taken is mv over bq. It's an important equation. So especially when you're talking about forces on moving charges. Now let's say in this room, the magnetic field is in this direction. Right? Let's say in this room, the magnetic field is from there to here. And if I shoot a charged particle this way, an electron, this way, just like this. So which way the electron is going to go? It's going to go taking turns, right? It's going to go around and around like that. So it's going to spin round and round. Now, instead of that, instead of shooting it like this, if I shot it like this, what will happen? Now, this velocity has two components. One is this component, and the other is that component, right? So what's going to happen is, due to this component, it's going to take turns with that radius. Because of this component, it's going to take round and round. What is this component going to do? It's just going to drift it forward. So what will be the final consequence? How does this charge appear to be moving? Like coil. Yeah. It'll just coil and go on. So if you shoot a charged particle, the charged particle is not going to go round and round. It's going to just keep moving forward because it's got a small component in that direction, so it will use that component and go forward. Right? Force between parallel current carrying conductors. Force between parallel current carrying conductors. So if you have an infinitely long wire carrying current, let's say the current is I1. And if you have another infinitely long wire, and that's also parallel to this, also carrying current, I2. Those are parallel current carrying conductors. Now both of them are actually sending currents in the same direction, parallel. What will happen to the wires? Will they attract or repel? What's your guess? We'll study it in detail, but just to guess first. There are currents going in the like directions. Will they attract or repel? No, there's only two answers possible, repel or attract. Okay, doesn't matter. Let's find out what happens. Let's find out what happens. Now, because of this current, is there a magnetic field in this neighborhood? Which way? How do you find out? Which rule to use? Right hand grip rule, yeah. Go back to right hand grip rule. Because of this wire, in this neighborhood, is there a magnetic field? Detect the current direction, detect the field direction. So, use the right hand grip rule. Pointing finger, the thumb indicates the current, and the magnetic field is going this way. So, at this location, it should be going in. I'm calling B1 as the magnetic field created by I1. Now is this a current carrying conductor in a magnetic field? So will it experience a force? Which rule? Which rule will tell you the force on a current carrying conductor placed in the magnetic field? Fleming's left hand rule. So pick up your left hand now and apply the rule. Magnetic field is in and the current is up. So which way is the force going to be? To the left. So this force on the second wire is going to be to the left. Now, think of it the other way around. Now, this is a current I2. Will this current produce a magnetic field in this neighborhood? Which way? Out. Look, when I put this thumb like that, you can just coil it around. You can see by the time it comes here, it's coming out. So it's a magnetic field that's coming out. And that is B2. Now apply Fleming's left-hand rule on this wire, on the first wire, and find out which way it will experience the force. Magnetic field is out of the board. Current is up. So which way is the force? So this wire is pulling the other wire, and that wire is pulling this wire. Now if this current is 10 amperes, and that current is 1 ampere, which force will be bigger? F2 is bigger or F1 is bigger?
F2.
What's the reason?
Didn't you say earlier that the bigger the charge, the more, the less the force is.
Yeah, I'm just waiting for other answers. Any other answers? If this is 10 amperes and that's 1 ampere, which force is going to be bigger? Which wire is going to experience bigger force? Yes?
F1 is going to be bigger because of the equation F equals EIL.
Okay.
If I is bigger, then this is going to be bigger.
But isn't this B smaller?
You're going to equal the same.
Why?
Because since the B is smaller on the left side, but the I is bigger on the other side.
Now,
B
can
is
you
bigger.
tell me why they should be exactly the same? What law in physics tells you that? Newton's third law. For every action, there is an equal and opposite reaction. If there is a magnetic force created somewhere, it should have a pair, and that is this one. This is the pair. Those two are exactly the same, no matter whether the currents are bigger or smaller. Yes, one of the reasons is this. As Joe said, magnetic field here is smaller than this magnetic field, but the current here is bigger than that current, so it kind of compensates it. So, yeah, these are Newton's third law pair of forces. F1 and F2 are going to be the same no matter what current is flowing in it. Okay, so just to mention that. So the forces are exactly the same, nothing is greater. Now, let's find out how much is this force. Obviously, you're not going to be able to find this force straight away. You know why? Because we don't know the length of this conductor. What did I say? A parallel, infinitely long. I didn't add that. Infinitely long parallel conductors get corrected. Because it's infinitely long, how much is this force F2? That's going to be infinity. Because according to the equation BIL, if L is infinite, it's going to be infinite. So it makes no sense there, like, oh, if the force is infinite on any parallel wires, that makes no sense. But that's what we are going to do is we are not going to actually focus on the total force acting on the wires. Instead, we will find the force acting per meter of the wire, per segment of the wire. So what is the force per meter? That's our concern. Force per meter. Okay, how much is the force per unit length? Force per unit length. Force per unit length. That's what we are interested in, not the entire force. So let's go. Can you tell, okay, now if the distance from here to here, if the distance between these wires is D, if the distance between the wires is D, can you tell me an expression for B1 created by this current I1? We've already gone through that. What is a magnetic field near a straight wire carrying current? You can turn your pages backward and find out. How much? So B1 is mu naught I1 over 2 pi d. That is the magnetic field B1. What is B2? How much is B2? Mu naught I2 over 2 pi d. Now, force on the entire wire is F2, which is equal to B1 I2 L. But we are not interested in the entire force. We are interested in force per meter. So force per length is equal to B1 I2. So substitute B1 there. What do you have? Mu naught I1 I2 over 2 pi d. And if you do the same thing on this side, F1, the force on this wire, is equal to B2 I1 L. So what is the force per meter on the first wire? It's going to be the same thing, mu naught I1 I2 over 2 pi d. So you can see that the forces are exactly the same. So that's a formula to find out the force on wires that are parallel to each other. You got it? Now if you have wires carrying currents in opposite directions, correct? If there are wires carrying currents in opposite directions, they will repel. Now you can actually check it out and see it yourself. If you have wires carrying currents in opposite directions, they will repel from each other. That's a good thing. So, because normally when you have wires for a certain application, the current has to come out from there, go into the appliance, go back. So which means they are in opposite directions. Can you see that? So in case they are nearby, they still will try to repel. They will try to repel but the force is not going to be severely strong if it is going to be if there is not much current, then the force is not going to be big. Okay? Yeah, so what will happen is this current produces a magnetic field here, which is inward. And that current magnetic field in and the current down produces a field that way, produces a force that way. And opposite is also true. When the current is going down in that wire, when the current is going down in the wire, the magnetic field here is in. Now apply left-hand rule. Magnetic field in, current up, forces to the left. So you can see that they are repelling each other. So in short, when currents go in the same direction, they'll attract. When currents go in opposite directions, they repel. Yeah.
What if everything's the same except for like the directions, it's the same force that's being applied.
Yeah, same. Magnitude is exactly the same. Mu naught I1 I2 over 2 pi d. That's a formula for force per meter, not on any conductor, per meter. So if you have a certain definite length, then you can just apply that. Okay, then it will be times that length. But the force per meter is going to be that one. Any questions? Mass spectrometer. There are different kinds of mass spectrometers. The one which we are going to discuss is a Bainbridge mass spectrometer. But again, it's not the spectrometer construction that we are really looking into. We are looking into the physics behind how it operates. Okay, what exactly is the principle on which it operates? That's what we are focusing on. So the main thing in the mass spectrometer is you need ions, and you need those ions to come with a certain speed. Okay? You can't just send any ion in. You need ions of selected velocities. Now, how do you choose those velocities? That's the first part. The first part of this mass spectrometer. Let me draw the whole thing, and after that you can do this. So the first part of this mass spectrometer is the velocity selector. How does the velocity selector work? And the physics behind it. Let's look into it. So what exactly is there in the velocity selector is that you have a pair of electrical plates. You have a pair of electrical plates. Now, if the ions are shot from there, if the charge of this ion is Q, and if it is sent from there down, now ions can be accelerated in a different way. That can be an earlier stage. We are not looking at that. These ions can be produced first and then can be accelerated. Maybe I'll show that also. So the ions are produced somewhere. The ions are produced somewhere, and then we have a positive potential applied here. Let's say if these ions are negative, if they are negatively charged. If they are negatively charged, then you apply a positive potential here with respect to the place where the cathode, and that will create a force on this because there's an electric field. So they will start moving fast. They will accelerate. They will accelerate from there, and they will pass through this. Inside here, they won't be accelerating. Inside, they won't accelerate. The reason? They are in an equipotential area. Once they're inside those cylinders, they are in the equipotential region. So they won't be an acceleration. Acceleration takes place only between here and here. So when these are going to come out from here, they are going to have a certain speed. Now, will all the ions have the same speed? all the ions, will they come with the same speed? No. All the ions won't come with the same speed because if they are charged differently, then they will accelerate differently. If the masses are different, then they will accelerate differently. So you can get a bunch of ions here. They're coming at different speeds, but we need to sort it out. We need to get only one set of charges to continue its journey here. You can't let everything to go through. So that's why we have. Now, if you put an electric field like this, and remember the charges that are coming are negatively charged. If you put an electric field here, and if you put a positive potential and negative potential, which way will these charges deflect? Which way will they deflect? This way? Now, will the deflection be exactly the same by all of them? No. They'll be deflecting in different directions. Like and maybe some, they'll be deflecting differently. Like they won't come straight, they'll start deflecting like this. The more massive ones will deflect less. The less massive ones will deflect more. Do you get it? Now, at the same time, if you put a magnetic field here, if you put a magnetic field facing outwards, if you put a magnetic field facing outward, facing towards you, so there's an electric field that way and a magnetic field that way, two fields. Now, what will these magnetic fields do to these charges? Okay, let's say this way. If I turn on the electric field only, which way will these charges deflect? To the left. If I turn on only the magnetic field, not the electric field, which way will they deflect? To the right. Watch. These are electrons coming, but these are negative charges coming down. That means the current is upward. Current is upward and the field is towards you. Right? Since the field is towards you, it's going to deflect to the right. Now, if you turn both of them on, what will happen is, if you turn both of them on, some will go this way, some will go that way, some will come right through the middle. So you will have some going like this, and some going right through the middle. Which ones are going to be coming right through the middle? That's what we are interested in. So what we do is we put a filter over here and select only the ones which are coming straight through. We put a filter here, a grid, a filter, and select only one velocity. So which ones are going to come right through is the one which experiences equal electric and magnetic forces. So the ones which are coming here will have the electric force and the magnetic force balanced. What's the formula for electric force? Q E. What's the formula for magnetic force? B Q P. Those are the two forces. Now the Q's cancel off. So do you know exactly which ones are coming here and with what velocity? So the ones which are actually coming through without being deflected, are the ones having this velocity. So if you know how much electric field you're applying, and if you know how much magnetic field you're applying, you know exactly the velocity of the ones which are coming through. So this is called a velocity selector. This is called velocity selector. This works on a simple concept. The first part of the mass spectrometer is the velocity selector. So we have the velocity selector. So what does the velocity selector do? The velocity selector is made up of two fields, an electric field and a magnetic field applied perpendicular to each other. So electric field and a magnetic field applied at right angles to each other. And what does it do? It applies a force on these moving charges to the left and right, depending upon which one's bigger. Now, if it has more charge, then electric force is going to be bigger. If it has more speed, then the magnetic force is going to be bigger. You get it? So if it has more speed, then the magnetic force is bigger. If it's got more charge, then the electric force is bigger. And so the ones which are coming right through the middle are the ones which are having one velocity. But they can be different charges, because you can see the charges are cancelling off. So you can have singly ionized particle coming here, doubly ionized particles coming here, triply ionized particles come. So you can have different ionization present on those things that are coming right through. So this is our first part. The second part of the spectrometer, so that's the first part of the spectrometer. And the second part of the spectrometer is that section. So what is happening over here in this section is we apply a magnetic field into the board, perpendicular. So all over this place there is a magnetic field. Was there a question of this one on ACT this time? Was there a mass spectrometer question? I thought I saw one like that. Huh?
There's like light spectrometer.
Oh, light, okay. Yeah, it's a very common question that can normally come through ACT test, because this is something that they can discuss. Yeah, so what will happen to these charged particles as it enters here? Which way are they going to get deflected? They are negatively charged particles. So current is that way, magnetic field is this way. So which way are they going to get deflected? To the left? They're going to get deflected to the left. So they'll get deflected to the left, and not only deflected, they'll go through a circular path. They'll go through a circular path of a specific radius. Which radius? We saw that just before this. What's the radius? mv over bq. So the radius of the turn, which is this radius, see? That's the radius. And how can you find the radius of this turn? Just find out where it lands, and that's the diameter, and then divide by 2, that's the radius. So the radius of the turn that is taken, is mv over bq. Now this b is different, okay, compared to that b. So let me call it b1. Let me call this b1, because there's a different b here. There's one b here, that's b. And this one is b1, which is into the board. So what is v? Substitute that here. So r is equal to m e over b b1 q. Now out of these terms, E, the electric field, is a constant, is fixed. B is fixed. B1 is fixed. The only things that are variables are M and Q. So what do you understand from there is, the radius of the turn taken is directly proportional to the mass. The radius of the turn is directly proportional to the mass. Now tell me, which charges will have the biggest radius? When it is singly ionized, or doubly ionized, or triply ionized? Which one is going to be taking the biggest radius? When it is? Smallest charge. So the ones which are singly ionized is going to take the farthest end, and all the others are going to get crowded here. Okay? You got it? Singly ionized, they'll go there. So if, let's say for example, you're taking chlorine, you know the isotopes of chlorine? There are two isotopes of chlorine. For chlorine, we have 17Cl35 and 17Cl37. These are the two isotopes of chlorine. And they don't come in the same proportion. In fact, these appear in the proportion approximately 3:1, the abundance. The abundance is almost 3:1. Like if you take natural chlorine, it's likely that 3 of those atoms that you picked up out of 4 are the 35s, and the other one is the 37. You've done chemistry last year. No, 2 years back. Right, so you must have gone. What's the mass of chlorine as it is normally written? 35.5 is around there. The mass of chlorine is around 35.5. Why is it 35.5? It's because you got 3 atoms of 35 versus 1 atom of 37. So you take the average. How do you take the average? Imagine 3 students got 35 points on a test, and 1 student got 37 points on the test. What's the average grade? 35 plus 35 plus 35 plus 37 divided by 4. It will be 35.5. So the average atomic weight or something like that that you have used earlier, it is actually taking into account all the isotopes present for that material. So on a periodic table you can see those numbers, they're all kind of decimals, and it's not like 35 or 37, it's like 35.5 something. So that is the mass. So there are 2 isotopes, significant isotopes of chlorine in natural chlorine. So if I take chlorine and ionize the chlorine and send it down here. So here comes the chlorine ions. Singly ionized chlorine ions are coming down here. Since it is singly ionized, Q is fixed. Right? Q is a constant. So what will happen to these chlorine ions when I send the chlorine ions? You will have this one coming down here, and you will have another one coming down here. So you will get 2 spots. Now what I mean by spot? This is a photographic plate. This part over here is a screen or a photographic plate. So when these ions come and fall on the photographic plate, it causes an illumination, a spot. So you can see the spot and then decide, like, okay, so one of them is landing here and the other is landing here. Which ones are landing here? Which one's got a smaller radius? Smaller mass. So the 35s are going to be here, and the 37 will land there. And you can actually see the relative brightness of this and this. This will be more brighter than this one. Why? Because out of all of them coming through, you have more coming here versus here. But you can understand that by comparing the radius, because radius is proportional to the mass, you can see that there are, so if everything is fixed, you can actually determine the mass. You can determine the mass because everything is fixed. You know E, you know B1, B, you know the charge, 1 electron charge. So you know the radius, you know the mass.
And those are the
Yeah, how does a loudspeaker work?
voltage gets translated into vibrations, maybe?
Yeah, ultimately it is that, but what is the physics behind it? What is exactly happening here? You don't see much from here. Now this one you should be able to see better. So yes, this is a diaphragm. And then the diaphragm is actually connected to, you can see a coil of wire. So the diaphragm is connected to a coil of wire. It's a circular coil. Now these things are more like a springy support and also to prevent dust getting inside. So you have a protection. You have a protection here to prevent any dust and all that going into the magnet. So there's a magnet. This is a magnet. Now that's a special kind of magnet, cylindrical magnet. You can see a hole right in the middle. So it's a magnet like this, like that. Yeah. It's a magnet is shaped like this. So the coil of wire goes like that. That's a coil of wire. And then this coil of wire is connected to the diaphragm. So that's a diaphragm that's supposed to be moving back and forth with the coil. Now from here, they're putting this thing to prevent dust and other things getting inside, and also to provide it mechanical stability. So they put this springy sort of fabric to protect. Now these are the wires into which the signal goes through. So when a signal is going through here, when a current goes through there, what happens is the current is going through those coils. And when the current is going through the coils, it is going through, and there's a magnetic field. So the current is going that way, and the magnetic field is down this way. So what will happen to the coil itself? It will experience a force. That way. You get it? So the current going like this, and the field going down, like north, south. So the field going down, current is going that way, current is going like this, and the field going down, the force is in that direction. So this coil, all the coils will experience a push forward, and that will push the whole diaphragm forward. Now, if the current is reversed, what will happen? The force is going to be backward. And if the current is alternating, if this current is alternating, then this coil is going to be moving back and forth, depending on the frequency. If this fluctuation of current is at a frequency F, then this cone, this diaphragm, is going to move at the same frequency. And when the diaphragm moves, it pushes the air particles, and therefore it creates sound. You get it? So you can see how the electrical signal is going into here, and the electromagnetic force is basically what is taking it back and forth. So if you just apply a DC current, then you'll see this cone going like that and stopping there, one way. Or if you flip the current, the cone will just go back. That's one way of testing whether the speakers work or not. If I want to know if this speaker works, I will just connect a battery like that. And you should be able to see the cone move. You see it move? Right? So when I put the voltage, it sends direct current, and that's why you can see the cone is moving one way. Well, these are not good speakers. That's why you hear if they're good speakers, then it should create one knocking sound. That's it. Yeah.
Could you explain the magnetic field direction?
The magnetic fields are between here, and so the coils are right there. Now it's actually happening everywhere, so it's not easy to see from all angles, but at least from one angle you can see it. When the magnetic field is downward and the current is towards you, like that, then the force is going to be in that direction. I can just pass this through quickly so you can look at it and send it. So you can see the slot where this one is supposed to go. It's all distorted. Okay. This is not the damaged one.